Welcome everyone to another edition of I Can Believe It's Not Better seminar series. Today we have the pleasure of having Matt Hoffmann as our invited speaker. As you may know, Matt is a research scientist at Google. Before that, he was at Adobe, and before that, he did a postdoc at Columbia University, and his PhD is from Princeton University. He's known for working actually many different areas, including some contributions to well, he's co-creator of STAN, the statistical modeling package. He has also extensively contributed to TensorFlow probability that many of you might have used. And yeah, his work on, as I said, on approximate inference. His work on stochastic variational inference and some also so for example, the no-U-turn sampler were both very influential in the field. And he also works on applications including music information retrieval, speech enhancement, topic modeling, and many others. So with that, I would like to let Matt take the stage. He will be talking about how not to use Bayesian inference to fine-tune your large pre-trained neural net. So Matt, all the stage is yours.
All right, thanks for the introduction, and thanks to everyone for showing up. I see even at least some people from California who hopefully didn't like get up early for this. Okay, so yeah, I'm gonna be first, thanks for the invitation. It's great to be here. I love the whole concept of this whole thing, and it's nice to sort of have an opportunity to give a talk that's not sort of like, look how awesome we are, look how great our method is. We crushed this benchmark and that benchmark, and everything is great, and it's so fast, and blah blah blah. And instead, just sort of like focus on something a little more process oriented and tell some fun stories. Yeah, this is going to be about some work we did about a year and a half ago now, where we got sort of interested in these large models that of course everybody's interested in now, and trying to tell some sort of like vaguely Bayesian story about how to fine-tune them. And this is work done mostly with Du Fan and Pavel Samsov in our group at Google Research. So in mid-2023, I'm sure I don't need to tell anybody that big models are a thing that like people are interested in. So at a high level, right, one version of this paradigm is you have some giant database of pre-training data that's not like the final thing that you're going to actually not the final problem or a set of problems that you want to solve, but it's a lot of data. And maybe it's supervised, maybe there are labels, maybe it's not. And so you do some kind of self-supervised or unsupervised. I'm still a little fuzzy on the difference between self-supervised and unsupervised, to be honest. But in any case, you pre-train some big model, probably a transformer architecture of some kind, on this big data set of pre-training data. And then you have this thing that hopefully is learned to become sensitive to interesting signals in this kind of pre-training data, and not too sensitive to uninteresting signals. So then when it's time to actually solve a problem, you have some much smaller set of labeled data or something like that that then you use to fine-tune this big model. So you copy the weights, you chop off the bit that was computing the loss for the pre-training task, you replace it with a new head that computes a loss for your fine-tuning task. You do supervised fine-tuning, and then you wind up with a model that is actually pretty good at whatever your task was. So in this talk, I'm going to be talking about we were playing with this vision transformer architecture, and it's sort of a nice example. Of course, large language models kind of become large language models and diffusion models have become more kind of the sort of thing that people are talking about these days. But the probably many of the same lessons kind of apply. So vision transformer is basically, the details are really not that important for this talk, but basically the idea is you chop an image into little patches and you just do a projection of those patches into some kind of like embedding that a transformer knows what to do with, and along with some positional encodings to tell it where the patch came from. You just shove it into an encoder, into a transformer, And then at the top of it, you wind up with some features that go into a simple multi-layer perceptron that does some classification task, right? So this is image class. This is extracting image features, and we have very large data sets of very large labeled data sets for images, and so we can do supervised pre-training instead of unsupervised or self-supervised. Okay, fine. So then for fine-tuning, what one would typically do is chop off the MLP head that was used in pre-training and replace it with a new head that just does linear decoding, or you could do something else, but that's kind of the easiest thing to do. Just put a new linear head on top where the old head was and have it solve whatever problem you're interested in solving, and maybe it's a different classification problem. Okay, a few details of what you might do there. So right at fine tuning time, you initialize the weights in the body with the pre-trained weights, you initialize the new head with a bunch of zeros, or I mean, you could use something else, but why? And I mean, yeah, I should say, right, there are a million variations on this recipe, but this is kind of the simplest version, and the improvements with the variations are pretty much at the margins. And then you just do, good old SGD on your new fine-tuning data, which is nice. It implicitly regularizes towards its initialization, so you can do this on the whole body without experiencing catastrophic forgetting usually, or you can just do it on the head, which is a lot cheaper, but may not work quite as well. Okay, so that's all kind of pretty standard background stuff. So now I'll talk about sort of what we were interested in and sort of what our hypothesis was about, why, what the place for Bayesian methods might be in this brave new world. Okay, so there is this very reasonable and I think widespread and I think reasonable kind of perspective that says that really these pre-trained models are essentially learned priors about what kind of things are interesting in whatever data modality you're looking at, right? And you see people use this kind of language all the time. For example, in this big tech report from a couple years ago from the Stanford Foundation Models group, they say, in language and vision, foundation models have demonstrated the capability to learn broadly applicable priors from large diverse data sets that can be subsequently adapted to downstream tasks, right? They're using this term pretty loosely, right? They're just sort of saying prior to mean broadly kind of like any kind of inductive bias or any kind of anything that encourages your model to do one thing, to do something that's sort of not in the fine-tuning data, essentially. Right, so like the fine-tuning data, there's lots of ways to fit it, and a prior is kind of anything that encourages you to fit it one way as opposed to another. Is kind of the way that they're using this language. But we were sort of like, well, okay, this makes sense, right? There's sort of prior knowledge, right, prior to the fine-tuning task at least, knowledge that is somehow stored in these foundation models or these large models. What if we kind of took that literally and did fully Bayesian fine-tuning, right? What would that mean? What would that look like? How can we do that? Intuitively, it sort of seems to make sense, right? That we have one source of knowledge, which is the pre-training, and we have another source of knowledge, which is the fine-tuning data. And it seems like, in some sense, the optimal way to combine those sources of knowledge has to involve Bayes' rule, right? Maybe. Okay, so here's sort of a first attempt at like a really simple version of what that might look like, right? We just take a model that is not kind of really Bayesian and put some priors on there and invoke Bayes' rule and see what happens, right? So we've got our feature extractor, which I'll call H. It's got some parameters theta, takes in data, spits out a feature vector. We've got our new logistic regression head. That's what's actually going to connect this to the new fine-tuning task. Totally standard logistic regression kind of thing, where you've got some weights, some regression weights beta, and those hit the features that were extracted by H and give you logits. And then the simplest, dumbest thing that you can do for a prior on our parameters, theta and beta, is just put spherical normals on them with some variance. Okay, this is like not particularly interesting or creative, but it's sort of an obvious first thing to think about. So what we actually did was we started with a head-only setup, right? So it's sort of a warm up. We said, let's set sigma theta to 0, right? Let's not fine tune the weights in the body. This is just a lot more convenient for a couple of reasons, right? We can pre-compute the features H, and that's not cheap, right? So it's great to only have to do it once. And then also, instead of having this like really gnarly Bayesian deep learning problem where we've got to think about how we're going to actually like sample from the posterior from the neural network, we've just got this really nice, friendly log concave Bayesian logistic regression. We know how to solve these. We've been doing that for decades. Great, right? So once we get that working, we can move on to the real Bayesian deep learning. And you know, spoiler, you know, we won't actually get that far. Sorry, but we'll learn some interesting things along the way. So what task did we look at? Well, we kind of looked at like what's the kind of dumbest computer vision task that you can look at. It's maybe CFAR10. MNIST is a little too dumb. That would be embarrassing, but CFAR10 is only like a little embarrassing. Actually, it's more embarrassing than it used to be. But so our base model is this vision transformer large, which is pretty big, trained on ImageNet 21K, which has I forget exactly how many, but like tens of millions of examples and trained with data augmentation. So you know multiply that by some unknowable factor. So it's a big model trained on a lot of data. And then we don't look at all of CFAR10. We just subsampled 100 examples for each of the 10 classes. So 1,000 examples total, 1,024 dimensional last layer features. And that's our logistic regression problem. Why look at this subset? Well, you know, for one thing, large models are often trained on fine-tuned on small data sets. So we wanted to kind of like be faithful to that. And then, you know, also there's kind of this Bayesian motivation, right? That the less data we have, the more important our prior should be. And, you know, we want to, you know, so that seems relevant. And also the less data we have, the more posterior uncertainty there is. And that also seems relevant, right? That like at some point we have enough data that there is no posterior uncertainty. And then why are you being fully Bayesian? I just noticed a question in the chat. Can you please explain the significance of sigma theta equals 0? Yes, so just setting the prior to a delta function centered on the pre-trained parameters. Exactly, right? So it's just not training the body, just leaving it where it was. And again, that's just for computational convenience. But I'll talk a little later about why I think that. So I'm going to get to sort of why this didn't work, and I'll explain later kind of why being Bayesian about the whole model I don't think would solve the problem that I'm going to talk about. Okay. So once we got the kind of infrastructure and feature extraction pipeline working, this was a really easy experiment to run. We just fit a baseline, which was a point estimate with regularized with weight decay, Gaussian prior map estimate, if you like. That does pretty well, 97.4 accuracy on the held out test set. Held out log likelihood of minus 0.0952, pretty good. So then we do the Bayesian logistic regression, right? So that is to say, we run Hamiltonian Monte Carlo on this targeting this posterior, generate a bunch of samples, and compute the probability, the predictive probability for each of those samples, and then average those to get the posterior predictive, right? The expected probability of y given x for the held out set, expectation under the posterior of that, right? Marginalizing out the weights. So held out accuracy is, basically the same, 97.3, basically, certainly not an improvement, maybe not a significant loss. But then the held out log likelihood is worse, like meaningfully worse, right? Minus 168 instead of 0.0952. That's not what we were hoping would happen, right? Like you're supposed to get something for being fully Bayesian, right? You're supposed to get better results. It's like harder, it's more principled. You're supposed to, you should get something for that. So, okay. So, but these are just numbers, these are just metrics. Maybe the interesting stuff isn't in the metrics. Maybe we could tell a story that's like, about calibration. Sorry, there's a question in the chat. Can you explain how you specify the prior again? It's just independent normals on the regression weights, and the variance of that prior was chosen just in the usual kind of like cross-validation kind of way. So it's not super sensitive to that, but yeah, we tried a few values of that for both the map and the fully Bayesian method, and basically a standard deviation of 1 was pretty good in both cases, pretty close to optimal. Okay, right. So anyway, maybe we can tell a story about calibration, right? Like, Bayesian models are maybe supposed to know what they don't know, right? And so maybe we can tell a story that's like, well, maybe the scores or the sort of like, scalar metrics are not so great, but actually we're better at knowing when we're not confident or something like that, right? So let's look at some calibration plots. So on the right is a calibration plot for the point estimate. On the left is calibration plot for full Bayes. Yeah, full Bayes doesn't look good here. It looks worse than the point estimate, right? What we want to see is that when we predict that there's like an 80% chance that this is a dog or whatever, then like 80% of the time when we make that prediction, we want it to be correct. So we're looking pretty good with the point estimate, and the fully Bayesian method is actually really underconfident in most cases, right? It says, if it says that there's a 50% probability that something is a dog, 80% of the time it's going to be a dog. So that's weird, right? What's going on there? Okay, well, let's do some model checking, right? Like that's the name of the game. You get results that you don't like, you ask why. So in particular, like, let's look at the data. We haven't done that yet. Okay, so what does that mean? Look at the data. Well, when you've got high dimensional data, I always like to do an SVD or an eigen decomposition. That's a good tool to reach for. Sometimes it tells you something, and in this case, it did. So if we look at the eigenspectrum of the covariance matrix of that should be h of x, not just x, right? The covariance matrix of our features. So that's the blue line here is the eigenspectrum of that training set. Sorry, it's sort of buried under the other lines. The thing to notice is that there are a lot of really, really small eigenvalues, right? So what that means is there are some directions that the empirical covariance for this training set just doesn't really have any variance in, right? There's just nothing going on in those directions. Now, if instead we do the same thing with the full 50,000 sample training set, a lot of that goes away, right? We have a much flatter eigenspectrum as it sort of gets out into the tails. It sort of like looks like this kind of, like the kind of like power law-ish kind of thing you might expect to see or whatever. It's much better behaved, right? Yes, X is the extracted features, not the original images. Yeah, thanks. Yeah, the original images would look quite different, but this is the 1024 dimensional features. Right. So then we also did, we can also do a thing where we say like, okay, is this like something weird about the data set, or is this something kind of more fundamental, right? And so what we did is compute the empirical covariance from the 50,000 sample data set, and then sample a fake data set that's just normally distributed with that same covariance, and look at its eigenspectrum, and that's the orange line here. And it looks like pretty similar to the eigenspectrum from this 1,000 example subset, right? So maybe this is a phenomenon that's not actually sort of about the data per se. Maybe it's about just like data with this shape in general, right? Not this particular data set. So sure enough, right? Okay, so we have 1000 by 1024 design matrix, right? Like that's singular no matter what. Like there's no way to get like 1024 directions worth of variance out of 1000 rows, but also, right, there are more sort of very small eigenvalues than you might have thought, or than I might have, thought without thinking about it, if that's a phrase that makes sense. So, right, purely by chance, my claim is that actually these very small eigenvalues are there purely by chance, right? This is not, this has nothing to do with vision transformer or anything. It's just a fact about subsampling. It's just a fact about matrices that are this size, random matrices that are this size. Right? You can generate a random matrix that's 1000 by 1024 with independent normal 0, 1 observations, right? So you know the expected value of the empirical covariance, right? The expected value is going to be the identity. Right, so that should have, just a totally flat eigenspectrum at 10 to the 0. And as you make that matrix bigger and bigger and have more and more rows, eventually you get an estimate of the eigenspectrum that does look kind of, as you would expect, it concentrates around what it should. But when the matrix is not that big, you wind up having some eigenvalues that are pretty big and some that are pretty small. And that's just kind of a fact about random matrices. So this is going to happen no matter what. Okay, interesting. So what are the implications of that? Well, so there was a really interesting paper that came out of Andrew Gordon Wilson's group a couple of years ago, around the same time actually, a little earlier, that was motivated by some work that we did with particularly Pavel Ismailov, and but also there were a number of other people from Andrew's group who were involved. Right, so a couple of years ago, we wrote this paper that was like, okay, let's bite the bullet and just like do Hamiltonian Monte Carlo, like real MCMC on a good size ResNet 50 on CPAR10 and just like see what happens, right? I'm tired of reading these papers about approximate inference, like, variational methods and so on for Bayesian deep learning. Like what would happen if we just like did the totally impractical thing and like tried to really sample from the posterior as best we could. It was an expensive experiment, but it was an interesting, but I think we learned some interesting things. And one of the interesting things that we found was that the Bayesian model average, right, the posterior predictive distributions or our estimates of them, were less robust to covariate shift than map estimates, than point estimates were, right? So this is a story that sometimes people tell about, like, why should we be doing Bayesian deep learning, right? Sometimes people are like, well, we should wind up with models that are robust when you give them data that's out of distribution. I think this is an intuition that comes from people's experience with GPs, Gaussian processes, right? With like, if you use like an exponentiated quadratic kernel, RBF kernel, whatever you want to call it, in a Gaussian process, then when you look at the posterior far away from the training data, it's just like, I don't know, like this is too far. I have no idea. Why would you expect me to know anything about that? It winds up not making super confident predictions about things it doesn't know, which is a legitimately nice property. And I think people kind of want that property to hold for Bayesian deep learning as well. And so sometimes we tell the story that we should have kind of better robustness to covariate shift, right? When we sort of go out of our comfort zone, that sort of data that are similar to the training data, we should be better. And that's not what we found. We found that we were worse, actually, which was, again, sort of a, head scratching kind of phenomenon. But fortunately, Pavel's smart and came up with what I think is a really convincing explanation. So they wrote this really nice follow-up paper, Dangers of Bayesian Model Averaging Under Covariate Shift, that made this really nice observation. So I'm going to talk about this in the context of like dead pixels, but it holds a little more generally to sort of dead neurons. But it's easy to see with dead pixels. So if you look at a data set like MNIST, right, there are some pixels in MNIST that are never anything but dead black, right? Around the edges, there are a bunch of pixels, like many pixels around the edges that just never do anything. And you know, it would be unwise or unwarranted, I think, to say that if there's something going on there, you should take it seriously, right? Or, I mean, I don't know, that's a philosophical question. You know, you could argue that maybe you should, like maybe that's a signal that you're out of distribution or something. But in any case, you should probably be careful about sort of, if you, like you, I think it's reasonable to say that you might not want a model that was sensitive to stuff that never happened in the training set. However, and if you do map estimation, right, if you do just standard weight decay, point estimation with, with SGD, with weight decay, in fact, you will wind up with a model that is completely insensitive to those pixels, right? Because, so on the right, on the lower right here, are some visualizations of the weights, the first layer weights in a multi-layer perceptron trained on MNIST. And in fact, right, if you look around the edges, they're not doing anything, right? And the reason for that is because they never did anything. And so there's no, the likelihood doesn't care at all what those weights look like. And so, and the prior would prefer, the prior assigns the highest density to weights that are at 0. And so if you're fitting a map point estimate, then you're just going to set all of those weights to 0. And so you'll wind up with like a literal blind spot in your model that, if anything, right, so now you do something out of distribution, right? You say maybe put some noise, salt and pepper noise or something into your test data. What's going on around the edges, that noise around the edges is not going to make any difference to your predictions, right? Because your weights are totally pruned, if you like. However, that's for the point estimate. The prior says that it's extremely unlikely, like profoundly unlikely, that all of those weights would be 0, right? That's just like completely inconsistent with the prior. The prior says that a priori, those weights are the same as any other weights. And if the likelihood doesn't care what happens to them, then the posterior over them should just be whatever the prior was. And the prior is a normal or something with non-zero variance. So that's sort of, there's a picture of something like that in the middle here, where you see, in particular, right around the edges, if you take samples from the posterior for this MNIST model, like you get stuff happening everywhere because the prior, that's what the prior expects stuff to be happening everywhere. So, the posterior should have stuff happening everywhere too, unless the likelihood is kind of vetoing that, which it's not. Okay, so then, right, at test time, what's going to happen? Well, if you apply it to MNIST-like data that doesn't have any variation around the edges, fine, nothing, doesn't matter, right? It's, it doesn't matter it really doesn't matter what those weights are. If they're the prior, that's fine. If they're 0, that's fine. But if you have some kind of domain shift, then where stuff does start happening around the edges, then you're going to wind up with these kind of models that say like, well, something's happening. I'm going to use these completely untrained weights, these totally random weights to influence my prediction. Because a priori, I thought that these weights should follow a normal distribution. A posteriori, I think these weights should follow the same normal distribution. Now something is happening there. And so I am going to put basically a totally random noise perturbation into my predictions here. And you'll get weird results, basically. Why did I say the likelihood doesn't care? Wouldn't the likelihood include a lot of instances where value equals 0, which should shrink the prior accordingly? What I mean by the likelihood doesn't care is that the weights, if you have an input that is attached to a weight, and that input is always 0, there's no variance in that input, and it's always 0 in particular, then there is no connection between, like, that weight could be anything and it won't affect the likelihood, right? Because it's just always being multiplied by 0. And then another question, on average, shouldn't the effects of dead pixels average out? Yes, sort of. They will sort of average out in a like linear regression model. They would absolutely cancel out, at least sort of an expectation. But in a classification model, there's nonlinearity, and so they don't, and so they wind up shrinking towards uniform. I'll talk a little more about that in a minute. If the test data is sampled from a different distribution than the training data, do we actually think Bayesian inference should do something sensible? I don't, I guess. But you know, I think it depends on the prior, right? Like if you're when you leave your training sort of distribution, you've got to fall back on your prior, I think, and that's in some sense one of the big messages of this talk. Is you know, we can't just assume that like Bayes' rule is going to fix everything for us, but we'll talk more about that later maybe. How sensitive are the BNN results to other forms of priors, non-normal / non-independent priors? Yeah, so that's a great question. I have a partial answer for it in a little bit, so we'll defer that, and then you know, ask again if you're not satisfied with that answer. How much do you actually trust the effective prior you're using here? I don't trust it. Again, that's the I think it's I think again, sort of the part of the point of this talk is that default priors will give you default results, and default results are, you know, may not be what you want, and that you know, in some sense, maybe the message is sort of like, if you want full Bayes to help you, you have to take your priors seriously, because the situations where full Bayes is most helpful are the situations in which, like the way in which full Bayes is going to help you is by correctly falling back on correctly specified priors. If you have poorly specified priors, then you shouldn't be surprised if full Bayes kind of bites you. Yeah, so it's not that surprising, actually. The Bayesian methods with a prior you don't believe in don't work so well. Yeah, and that's, you know, I think that's a lesson that, you know, that we all maybe need to learn, kind of, in some cases, at least in my case, sort of over and over again. Okay, all of these are great questions. Some of them, hopefully, yeah, I'll address more in some of the following slides. But thank you very much for all these questions. Okay, so what's my explanation now for why we're seeing these bad calibration results and these bad log likelihoods? Basically, we're in a similar kind of situation to the dead pixels world, where the likelihood, right, our logistic regression likelihood doesn't care much about the projection of its weights beta onto the like almost null space of the features in the training set, right? If there's nothing going on in some direction in the training set, then the likelihood is not sensitive to what your weights are doing in that direction. And if the likelihood doesn't have an opinion about what the weight should be doing in that direction, you'll just revert to the prior. The problem is that those low variance directions are only low variance in the training set, not in the population. They're low variance not for any good reason, just because of sampling noise. Now, at test time, we have, you know, we sample from the posterior. We have an ensemble of models, each of which is sensitive to these rotated features that just weren't in the training set. And so they're sensitive in a totally random way, right? One of them, if you have some variation in one of these directions that it wasn't really trained on, you can say like, oh, for sure that means this is a dog. Another one can say, you're crazy, for sure this means it's a plane, whatever, right? And the reason is because like they just had to make a random decision, right? A priori, your prior said you should be sensitive to pretty much everything. And if you see variation, it should mean that you are more confident about your prediction, because that's how linear models work. And so at least for, that's how logistic regression models work anyway. So what this is going to wind up doing, right, you have this ensemble of really overconfident models that are making essentially random predictions or semi-random predictions. And that's going to shrink the ensemble prediction toward a uniform distribution, which is where this underconfidence is coming from, right? It's saying there is some chance that, something totally random is the right model. And on average, the totally random model is uniform, makes uniform predictions. So that's the sense in which the effects of these sort of dead pixels, if you like, average out. But they average out in a way that is not neutral, right? They average out in a way that shrinks you towards a uniform prediction. Okay, so what can we do about this? Well, if the problem is that there are all of these directions that we can't learn from, what if we just got rid of them, right? Let's do principal components regression, right? Do PCA, throw out the smallest eigenvalues and or the least significant directions, the lowest variance directions, and then just do logistic regression in that space. Okay, that's easy to do. Let's take just the top 20 eigenvalues, right? If you look at the right side of that eigenspectrum plot from before, right? You see there's a lot of action in on the far right side of that plot, and also like we're able to estimate those things pretty well because there's not a lot of them and they're pretty high variance. So fine, right now at the bottom here, I've added results for this Bayesian logistic regression where we do it on the PCA, the 20-dimensional PCA space. Works pretty well. Maybe we take a little hit in accuracy, but we get a nice improvement in held out log likelihood. Still not as good as map, but something. Calibration looks certainly much better than the plot on the left, right? The plot in the middle is with the PCA. Maybe it looks better than the plot on the right. Maybe it doesn't. I don't know. Like it looks sort of better towards the middle, maybe not quite as good towards the bottom. I don't know. I mean, these are not big differences. Fine. Okay. But that's like a little bit of a blunt instrument, right? That's like a little, we're saying a priori, now we're, right, that's sort of saying a priori, like, I am totally sure that there are, at most 20 dimensions that are relevant. And I don't know, that's kind of weird. Also, it's not really clear how you would do that. It's not totally clear how you would do that if you were to do everything end to end, right? But maybe you could. So okay, let's be Bayesian about this and do some kind of like Bayesian variable selection thing, right? So again, we're going to use this rotation matrix U to whiten the feature space, and now we're going to introduce this soft mask variable MD, one for each of the principal components, that follows a beta distribution with parameters 0.05 and 1. So the expected value of this is about 0.05. And there's a plot of its density on the right. Right, so it puts most of its mass near 0 and then spreads the rest out sort of between 0 and 1. So what this is saying is that we think kind of most, and right, and so then we multiply these this mask by the appropriate column of beta before applying the logistic regression, right? So this is basically saying there's some dimensions that we think are relevant and some that we think are not relevant, and we're going to figure out which is which. But in a soft way so that we don't have to mess around with like spike and slab priors, which are just kind of a nightmare. And if you want to, you can sort of think about like marginalizing out mu and thinking about this as sort of a prior on beta where it depends on x via this rotation matrix U. Okay, so now I've added some more results at the bottom here, which I'm calling soft PCA. And kind of the headline numbers are, competitive with the hard PCA, where we got rid of all the 20 of the principal components. Still definitely not beating map. But there's some sort of nice, some nice intuitions here, right? If you look at the at how the posterior mean, or our estimate of the posterior mean of these mask variables changes as a function of which principal component they're attached to. For the ones with small, I should note that there's a significant amount of noise in this plot, right? Because this is an MCMC estimate, so there's like just Monte Carlo noise in here as well as actual posterior variation. Sorry, in addition to like actual, I think most of the sort of fluctuations here are just Monte Carlo noise. So if you look at the left-hand side of the plot, as we would predict, right, these are the smallest, the least significant principal components, right, the smallest eigenvalues. So the likelihood doesn't have much to say about what this mask should be doing, and so sure enough, it reverts to prior, and the prior says, well, about like 1 out of 20 models should care about this direction. So that seems to be happening. And then as you go up and look at the higher variance directions that are not relevant to the task at hand, but do have some significant variance attached to them, now the posterior is getting more confident that actually, we should really be masking these out because they're not helping us. And so you see this sort of fuzzy blue line kind of dipping underneath the prior, the level you would expect a priori, as you go to the right, until you get all the way to the right. And then you see that there actually are a handful of directions that do remain sort of unmasked. And in fact, if you look close up, there's sort of 9 all the way to the right there, and then 1 a little bit less to the right. So in fact, the model has kind of decided that basically there are like 10 directions that matter here, which maps pretty nicely onto the fact that there are 10 classes that we're trying to estimate. So, maybe the lesson here is that the vision transformer trained on this ImageNet data, kind of already knew about all of the CFAR10 classes and actually kind of like was already explicitly encoding those, already has features that explicitly encode like those 10 CFAR10 classes, quite possibly. Although they're not axis aligned, which is annoying. And then if we look at calibration, it looks similar to all the other things. It works fine. Okay, fine. So, maybe that's like a little more satisfying of a Bayesian story than the like, let's do PCA and then do Bayes. Or maybe it's not. Because we still have to, this rotation matrix is still coming from, still coming from an STD basically, which is maybe a little unsatisfying. Again, if you were to think about the thing where you're trying to train end to end, like, you really want to be doing like an SVD, you like really want to try and tell a story about how that SVD is like really part of your model, how like your model is like, there's this training set X, and then I have this prior on the vision transformer weights that extract some features. And then before I like actually, but right then I'm going to like extract those features from the whole data set and then do an SVD on the resulting design matrix and then rotate them based on that in this sort of like batch normie kind of way ish, and then do the logistic regression. I mean, you could, it's a story, you could, it's coherent, it's a generative process, but it's a little weird. But you could do it. There's other things you could do too. Okay, fine. But anyway, the takeaway here is, we did some stuff. We did the obvious thing. It was way worse than the stupid thing, which is just to like do gradient descent and computer map estimate. We worked hard to understand what was going on, and were able to get results that were almost as good as the dumb thing. Okay. So, not like a huge one. But hopefully an interesting, certainly an interesting experience, and hopefully sort of interesting story. Okay, so as I was saying earlier, right, what have we learned, right? Prior elicitation is important, right? The Bayesian formalism, I do believe this. The Bayesian formalism is coherent, right? If you have a relationship between inputs and outputs, that is not misspecified, and there's a problem with full Bayes, then it is a problem with your priors. And I do think that, we can't be that badly misspecified here because we're getting like 97% accuracy. So kind of the extent to which you can say that a model that is 90% accurate, 97% accurate is misspecified is, I mean, I think that's a tough claim to make. Okay, so there's a problem with our priors, right? And so, what's wrong with our priors? Or when we were using this default prior, the standard normal, that's expressing a very strong belief that the correct model is not sparse, right? A priori, the chance that there's any kind of interesting sparsity, zero. There's just no way. And unfortunately, the rotational symmetry of the transformer architecture means that the relevant features that we're interested in are just not axis aligned in any meaningful way, right? So if you look at the top 5 principal components, this is this plot in the lower right, they're all over the place. There's no sparsity to be found anywhere here, right? And so there's lots of structure, definitely lots of structure, but it is not axis aligned. And so the sort of obvious sparsity inducing priors that you might slap on this model are not going to work. They're not going to do anything useful. Vincent asks, do you think something like the Laplace distributions of prior might encourage some sparsity and work better? Right, and I sort of discussed that. So, yeah, I think it. So Laplace distributions do, or a horseshoe prior, right? Yeah. So the horseshoe prior I think is going to work better if you're being fully Bayesian. Right, a horseshoe prior is sort of like a better fully Bayesian sparsity-inducing prior than a Laplacian, right? Like there is sort of this story that the Laplacian sort of corresponds to L1 regularization, and that story is true insofar as it has heavier tails than a Gaussian, but I think it's misleading insofar as the sort of hard sparsity that you get out of an L1 prior is an artifact of the non-differentiability of zero, which full Bayes doesn't really care about at all, right? Because the amount of mass that's around that non-differentiable spot is zero. So there's sort of, right. And I guess I would also say, like, you could also use right, to here I'm using this, this sort of soft mask thing. If you integrate out that mask, then you'll get something that looks like not so different from a horseshoe prior, I think. It's not exactly the same thing, but it's very much in the same spirit. Okay, so that's sort of, so I guess my claim is like, the reason this didn't work is because our priors are wrong, and just using some like independent axis aligned default thing is not going to help. Another important lesson. Okay, yeah, one more question. Can we think of the naive SGD method as implicitly incorporating a sparsity prior, since it probably only changes the weights from initialization in a few top eigendirections? Yeah, absolutely, totally. It doesn't like, it's not clear what that prior is, right? I can't write it down. It's that prior is like, it's probably not coherent in the sense that like, it's going to like, it's not the same prior for different data sets, right? So it's going to give you different behavior. It's going to have a different inductive bias for different data sets and likelihoods, which is kind of like not coherent in a Bayesian sense. But I mean, who cares, right? Like if it works, then that's great. I mean, the other thing it won't give you is uncertainty, of course, which maybe we care about. Right. So another sort of thing I want to just like kind of get on my soapbox about here is there is no such thing as an uninformative prior. This is like language that we use sometimes, and it's I think it's harmful in a lot of cases. Right. So we think of like, sometimes we think of like higher variance or heavier tailed priors as being less informative, and I think that can be misleading. And I think like in this case, it's, the reason I think that's misleading is because in high dimensions, you you know, I think it's fine in low dimensions, right? If you have like a 3-dimensional problem, you can talk about uninformative priors all day long. That's fine. Our intuitions work there. In higher dimensions, I think it doesn't make sense, right? In higher dimensions, if you say I'm going to increase the variance of my prior, I'm going to make it super heavy-tailed or something, that's expressing a very strong belief about, for one thing, the norm of your parameters, right? And that's something that, you know, if the likelihood isn't informative enough to overwhelm it, then that's going to really make a big difference in your predictions. So you know, so I did a little experiment here where, like, you know, what if we increase the scale of prior by a factor of 10? The answer is nothing happens. Nothing really changes. The log loss is worse, right? You get sort of worse behavior at the tails, but I think that's actually kind of just an MCMC, a failure of MCMC to generate kind of enough samples. I think that's actually just sort of like a Jensen thing. Right, and basically, I think even with the standard normal prior, we're in a situation with this model where all of the posterior predictive uncertainty is epistemic rather than aleatoric, right? So what I mean by that is that our logits are large, right? So what winds up happening is for any sample from the posterior, we wind up with logits that are large and therefore have, right, like less lead to more concentrated predictive distributions. And you know, the difference between being sort of like 99.9% confident and 99.999% confident is not that significant compared to the uncertainty that is due to not being sure about how to interpret variation in directions you've never seen variation in before. Right, so all of this uncertainty, I claim, is the result of our ensemble of overconfident models disagreeing about what they're overconfident about. And that's not necessarily a bad thing, right? Like, I think for a CFAR classification problem, it's totally appropriate to have your posterior predicted distribution be an ensemble of overconfident models, right? Because we know that this problem is not that hard and that the correct model is going to be very confident, right? Because the problem isn't fundamentally that hard. But, you know, anyway, the point is just that, like, you can't just make things uninformative by increasing variance. That's enough about that. Okay, questions. This phenomenon also exists in other domains such as texts. Good question. I don't know. I'd like to know. I mean, it should, right? Some version of this phenomenon should exist for text. There's nothing vision specific about this issue that I've described, at least sort of as I understand it. But I haven't done the experiment. Kevin says, magnitude of the weights and hence posterior variance magnitude matters more for regression than classification because of softmax. I agree with that. That regression and classification, because of the nonlinearity between the linear function and the sort of natural representation of the predictive distribution, which I use natural in the intuitive sense, not in the exponential family sense. Yeah, could be quite different for classification than regression. And we've definitely seen that when we've looked at regression. So there, right, having really large weights or having a really high variance prior on your weights is very informative in the sense, it's still very informative, right? It's still highly informative in the sense that you're saying that a priori, I really expect my function to vary all over the place. But on the other hand, that's a situation for regression. The likelihood can kind of tamp that down a bit, at least, in directions that it's seen before, at least. Right, it's going to say that, you know, you shouldn't make things really large, whereas classification, you don't have that phenomenon. Is an appropriate interpretation of this story saying the priors would work in the more classical lower dimensional regime, that would work in the more classical lower dimensional regime, fail in deep learning due to the effects of very high dimensionality? Yeah, I mean, I think the default priors, I think I would say that default priors that work well in sort of like n significantly larger than p, so to speak, right, where you have like a good number of observations relative to the number of dimensions you have. Yeah, default priors can work fine there. I think anytime when you take a step away from that regime, whether it's, right? I mean, this is not a deep learning story, really, right? I didn't actually do any deep learning here, except for like the feature extraction stage. This is all shallow, right? So it's just a question of sort of like, but yeah, I mean, you know, it's certainly as much of a problem in deep learning or more when you have like significantly more parameters than observations. Okay, right. So we sort of talked about this a little bit, right? You know, gradient descent is like actually a pretty good heuristic. You know, it's got this sort of greedy effect where if it ain't broke, don't fix it, right? Like SGD, if there's nothing going on, it's not going to do anything. And sometimes doing nothing is the right thing. And then, you know, if you just do like weight decay and point estimation, right? Sometimes you get like really nice sparsity inducing behavior. And then like early stopping is a cool heuristic too. Again, like really effective regularization, really great deal. Does not have a clear coherent Bayesian interpretation, but it really works. And all of these methods have the property that you don't actually have to identify what are the relevant or irrelevant directions, which is really nice, really nice property. You know, it's not, it is not a coincidence that people are using gradient descent for everything all the time these days. It's a really good algorithm. Okay, like I said, this is all a story about like actually a really shallow learning problem, not deep learning. So you might ask, like, what if we actually were a little deeper about this and tried to fine tune more layers? My claim is that that won't fix the problem, right? The issue is that the posterior over the features, right? For that to solve this problem, right, what would have to happen is the posterior over the features, fine tuning the model in a Bayesian way, would have to eliminate these weird directions that have no variance in the training set, but do have variance in the population, not only in the training set, but also in the population. And I guess I don't see any reason to expect that to happen. Right, if anything, I think it should get worse. Will the problem go away if we have enough data? Yeah, this problem will anyway. But if we have enough data, at some point, like, why are we being Bayesian? Right, like, you know, if Bayes isn't shining in situations where the data aren't strong enough, where the likelihood isn't strong enough to like aggressively constrain our inferences, like, why are we being Bayesian? I mean, there might be answers to that question. It's not just a rhetorical question, but you know, maybe it's something we should think about. So yeah, right, yeah, and here we are. So just some more, you know, a few more questions, and I'll wrap up. Was this the wrong test problem? Right, does full Bayes actually need more data than math? That's like contrary to everything I've ever been taught, but maybe it's true. You know, some of these have come up, right? Like, is language different than vision? Maybe. I mean, I think, like I said, I think this problem is like a pretty abstract mathematical phenomenon rather than a kind of domain-specific thing, but it could be that there are important differences. CFAR 10 just dumb, right? Like, would this have been more interesting if we worked with, I mean, we did try CFAR 100 and it was not more interesting, but, you know, maybe like classification problems, they're really close to the ImageNet problem that the vision transformer was trained on are just like, this is stupid. Like, we shouldn't be doing that. Maybe there are more interesting problems out there, like, you know, like harder problems like segmentation or something. Is this the wrong way to operationalize this large model as prior intuition? It's the obvious way, I think, right? To say you've got a model and I'm going to put priors on its parameters, but maybe there are other ways. Maybe we could improve the results by learning a prior across multiple fine-tuning tasks, right? Maybe the problem is that, you know, maybe it's hard to specify a prior just by pure thought, but maybe we can learn something by looking at a bunch of different fine-tuning tasks, right? So not just sort of like the large model is itself the prior, but also like maybe we need to do some pre-training of that's about the relationship between that large model and the kinds of tasks that it's going to be used on. I think that could be interesting to look at. And then, you know, there's also this subject of distillation, which it feels like Bayes should have something to say about, right? So if you want to put one of these things into production, you'd prefer not to serve a giant model. If you don't have to, you'd prefer to serve something specialized that performs as well as a giant model, but is much smaller. I don't know. I think there's interesting things to think about there, but we haven't really, generated any amazing insights yet. So yeah, I'll leave it at that. And there have been lots of really great questions already. But if people have more and want to stick around, then I'm happy to talk more.
Thank you, Matt. It was very good talk. I really enjoyed it. I'm also glad to see that there were so many questions from them, so much audience engagement. I think we broke records of the seminar series. I do have I encourage the audience to post maybe it was time for 1-2 more questions. In the meantime, I wanted to ask this problem that you mentioned, when you were describing the issue of the dead pixels, you said there was some generalization that was possible. I didn't really get what you mean. Do you mean that even if the problem is not just on the input space, but on a kind of feature space where you don't have these exact zeros, it's just about the value of the eigenvalues? Is that what you meant, or you meant something else?
Yeah, exactly, right. So if instead of right, so it's sort of easiest to visualize for the input space, but it could equally well apply to features in the hidden layers. Right, there's some presumably there aren't a lot of literally dead neurons, right? Presumably there aren't a lot of hidden units that are just always dark in these models, but there could certainly be directions, again, for smaller data sets at least, there could certainly be directions where the in the sort of hidden feature space where there's very little going on.
That makes sense. Thank you. I think there's another, you've been already checking the chat, but I can read it out loud from Yukon Park. Will making the body or the representation stochastic alleviate the problem? It might be less likely that there are dead features.
Yeah, that's a really interesting question. So I think the answer is probably yes. In a sense, right, that's sort of like, you can sort of look at it as almost a data augmentation thing, right? Where if the problem is that we have a small data set, if the problem is that we have a small data set, and so our design matrix is small, and so it has these this sort of quasi null space that's large. The obvious solution is to make the design matrix not so small. And one way to do that might be to throw a little bit of noise into the transformer, drop out or whatever, and that should increase the amount of variation that we see in the last layer features, and maybe address the problem to some extent. I think it's an interesting hypothesis. I do think that computationally, being Bayesian about stochastic features is hard, right? That in principle, you can do things like stochastic gradient Langevin, but they tend to behave pretty differently from really, but there tends to be a pretty meaningful difference between the results you get from that and what you get with a non-stochastic MCMC method. And so I would be a little concerned about that, but maybe there's a way to make it work. Maybe using pseudo-marginal MCMC or something. If you have some freedom in how you specify the relationship between the noise and the likelihood. So maybe you could do something there. Maybe it would be hard. No. But it's a really interesting question. Let's see. Kevin Murphy asks, could we just do random projection on H of X and then do Bayesian logistic regression? Maybe. Let me think about that. So, right, random projection is going to be, I guess, what you would need to do, right, is you would sample some random directions and project the features onto them, and then do logistic regression there. And I think the question is whether there would be a, whether, right, if the problem is that we are seeing sensitivity to directions that were not in the training set but are in the population, the question is, would that variance make its way into these random projections? And I think the answer is maybe. I would want to sit down with pen and paper for a minute to answer that question with confidence. I'm not sure that there's a sort of linear solution to this problem, but maybe. Okay, regarding utility of Bayes, even if SGD does better in terms of log likelihood, what about sequential decision-making tasks where joint predictions across multiple test points matter more than single point predictions? Great question. Yeah, love it, love it. I love it when people are, yes, I think the right, the real utility of Bayes is, may just not be like knocking out these scalar benchmarks, right? But it might be subtler kinds of decision-making kind of tasks. That sounds very plausible to me. Yeah, so for example, I could imagine there being like an active learning story, something, right? Or like, maybe your fine-tuning data set starts out really small, and then you like select new observations to get expensive labels for, or something, or something like that, maybe. I mean, I think you're still, it's right. The fact that these predictions, the fact that these like single example predictions are poorly calibrated, I think is not a great sign. But maybe, yeah, there might be some other sort of subtler way of evaluating, some better task to evaluate on than just sort of like, standard point-wise classification accuracy or log loss or something like that. I think that's a really good question.
Cool. So I think this is a good point to conclude. And thank you, Matt, again. Like it was really good. And I hope everyone enjoyed the talk. And also, like, remember that we have a mailing list that you can join if you want to get notifications about future events and of I Can Believe Not Better. So yeah, thank you, and yeah, have a nice day, everyone.
Yeah, thanks so much for the invitation. Thanks to everybody for the great questions, and thanks for coming. This was fun.